All wireless systems have this weakness, be it Wi-Fi, Bluetooth, smartphones, radio, satellite TV, etc. Interference from other services is often very persistent. Today I will explain the root cause and how to fix it. In the last episode, we looked at the safety limits for human RF exposure. We have seen that in everyday life we rarely get to these limits unless we hold our mobile phone directly to our ears. Today it is about the so-called electromagnetic compatibility of radio systems with each other. And here things are very different. There can be actually many potential problems that we have to take into account. This field is also regulated so that many different radio services in the world and in space can function smoothly. In addition to the desired signal, wireless systems and electronic devices also generate undesired emissions in a wider frequency spectrum. They are also called spurious emissions. There are limit values for this. For example, the level of unwanted emissions caused by a transmitter must be 40 to 60 dB lower compared to the carrier signal. In addition, the unwanted radiation level from an electronic device must not exceed a certain limit at a distance of 1 meter. This could be caused by the clock frequencies of microprocessors or switched mode power supplies and their harmonics. It also could be a microwave oven, because a small part of its microwave energy always escapes and is therefore a potential interferer. So we have to realize that if a sensitive receiver comes too close to the set devices, this alone could lead to interference. In addition to that man-made noise, there is also noise from natural sources. In the lower frequency range there are atmospheric discharges. In the upper frequency range our sun plays a role, which emits also radio noise besides other radiation. Unfortunately, the receiver itself also causes interference. Like any technical device, the receiver has limited dynamics and selectivity in the frequency domain. A strong adjacent signal can block the receiver as a result. Typically, the blocking resilience of the receiver is up to a signal level of 0 to 10 dBm. Of course, it plays a role whether the interference signal is in the receiving band or not. Then there is a second effect in the receiver that is much more serious. And that's what I want to talk about today. It's called intermodulation. In short, in the receiver we find a frequency mix due to slight nonlinearities. And the resulting frequency mix products can fall exactly on the receiving frequency. Intermodulation can be caused by significantly smaller interference signals than for blocking. Typically, the intermodulation immunity in the receiving band is specified at -43 to -24 dBm. Potentially, intermodulation interference can happen over long distances therefore. This often makes the situation already difficult to analyze. In addition, there is a large number of intermodulation products. This list applies to only 2 interference frequencies. If there are more than 2 potential interfering frequencies, then the number of intermodulation products literally explodes. I thought I'd put practical scenarios on a graph so we can understand it all better. I'm basically using the same graphics as in the last video, where we also looked at the power density of radio signals. However, the radiant power density range in this graph covers 22 orders of magnitude. We can use it to enter practically everything that happens in the range of usable radio waves. At the top, we have the safety limits for humans for orientation. The signals that appear at the bottom are really damn small. Before I come to our example of intermodulation, I would like to briefly show what you can do with it. First, I want to show you what the bandwidth of a receiver does. We now enter 0.1 MHz for the receiver bandwidth. Now appearing below is a yellow band representing the noise signals from the sun and a gray band roughly representing the man-made noise. I have presented the worst case scenario here, which occurs when there is high solar activity. Now let's change the bandwidth to 5 MHz, which is the bandwidth of a TV SAT receiver. We immediately see that the noise level increases with the higher bandwidth. I will link you to a video in the top right corner in which I explain why this is the case. Next, we enter our receiver temperature of 27 degrees Celsius and we immediately get the receiver's intrinsic noise level displayed as equivalent radiated power density. Strange! Why isn't the level constant over the frequency range? It's simply because we have normalized the equivalent radiated power density to the isotropic antenna with 0 dB antenna gain. Due to the fact that the isotropic antenna's effective area decreases with increasing frequency, the radiance must increase in order to get the correct noise level for a given frequency. While we are at it, let's also say that the receiver needs an SNR of 15 dB in order to be able to decode the TV signals. Now we turn on our geostationary TV satellite operating at a frequency of 10 GHz at an altitude of 36,000 kilometers. Unfortunately, with geostationary satellites, the sun can be behind the satellite for a few minutes a year. Maybe that's a problem? Let's take a quick look at our Excel graphic to see how this works. The satellite transmits with an effective radiation power of 80 dBm. This can be achieved with a few watts of transmission power and a parabolic antenna. The satellite signal now appears as a dot in our graphic. Unfortunately, the signal is barely stronger than the noise of the sun. On the receiver side, we now also use a parabolic antenna with a gain of 40 dB. What does the graphic want to tell us now? The answer is, we can receive the TV signal well, as long as the sun is not in the main beam direction of our receiving antenna. Well, that's mostly not the case. But it does happen on a few days of the year and then for a few minutes each time around lunchtime. Then the TV reception is actually disturbed by the sun for a few minutes. So now we go back to the no sun scenario. Now let's assume that two weak data transmitters are placed nearby on the roof, which work simultaneously for several hours every day. Their transmission power is only 20 dBm, i.e. 100 milliwatt. Due to the low transmission power, it is assumed that there should be no problem. Is that right? Unfortunately, the television reception is often disturbed. We need to take a closer look. First of all, we would like to see where the level for intermodulation interference of our satellite receiver is. We enter the intermodulation resilience level of -43 dBm here. We then get two curves, namely the upper line, which applies to 0 dB antenna gain, and the lower line, which applies to the antenna gain that we specified for the receiving antenna. And this means that the upper line applies to an interferer outside the main beam direction, and the lower dashed line applies to an interferer in the main beam direction of the antenna. Then we have the two transmitters with only 20 dBm transmit power in the vicinity of our TV satellite antenna. They transmit on the frequencies 11 GHz and 12 GHz and are 2 meters and 3 meters apart. The frequency of a third-order intermodulation product results from 2 times 11 GHz minus 12 GHz is exactly 10 GHz. In our chart, we immediately see that the signals are above the critical limit. And this means that the two weak transmitters can actually interfere with our TV reception. This is simply because the two frequencies are just so unfavorable that a third-order intermodulation product is exactly on the receiving frequency of the SAT receiver. The regulatory authorities try to avoid such problems through clever frequency regulation. However, due to the numerous intermodulation products, the problem occasionally occurs, especially when devices are defective or are operated in illegal frequency ranges. If you have EMC problems, what can you do? Filters can help to improve a receiver's selectivity and thus weaken the interfering signals. This could be realized with a bandpass or a notch filter in the antenna feed line. Another very elegant method would be a selective antenna. I've shown this before for a LoRa link. I will link you to the video on the top right. The interference does not always come via the antenna. It could be also received on the intermediate frequency. In the event that interference signals are coupled to a SAT cable, a better shielded cable can be used. Sometimes a filter in the power supply can also help. It may be possible to increase the wanted signal and reduce the interference signals by changing the location. A directional antenna is always a good idea to achieve this, because a stronger useful signal is less likely to be interfered. The insights. EMC problems are always annoying. They happen despite a lot of regulation. I hope my video helped you to understand the reasons for this better. Spurious emissions and receiver blocking problems can usually be found and eliminated very quickly because the interferers are in close proximity. The cause of intermodulation is usually not easy to find because the interferers can be far away and many combinations of potential intermodulation products have to be checked. You may have to take some of the measures proposed to ensure that radio receivers are not interfered. If you're interested in such topics, then stay tuned. We will be posting videos on these topics from time to time. See you soon in the coming episodes.